Thanks very much for the invitation. So there was a good bit of scene setting around land use change and food and so on, and that's one of the things I'm going to try to talk about. But of course it's really about whole systems analysis of bioenergy value chains. So what are we trying to do in this project? We're trying to understand from a systems perspective what biomass technologies might be the ones that are relevant in a UK context. How does this issue of competition between producing biomass and using land for other things play out under different scenarios? Understanding how cost reductions and other system implications will again play out over time. And then looking more specifically from a policy perspective, looking at if the UK wants to have a serious proportion of bioenergy in its energy mix, what would it take in practice from the perspective of the mobilization of a value chain all the way from producing cultivars, growing crops, harvesting them, the logistics system and the end use technologies. And all of that is going to be done within a context of a variety of different kinds of evaluations. So not just economic evaluation and not just greenhouse gases, but also a variety of other evaluations. So these are some of the key elements in our project and in our modelling framework. First of all, to try to understand the UK not just in a domestic context but in a global context, and to look at it from the point of view of what can it realistically access in terms of food and different kinds of biomass with different kinds of degrees of processing, raw biomass, finished products like fuels or anything in between. Coupling the UK energy system model, which is being developed at UCL, which is a whole energy system model, so it's got everything in there, renewables, nuclear, fossil fuels and so on, and coupling that with our detailed bioenergy system model to look at the soft coupling between these models and how the two things can actually lead to conclusions which you wouldn't get if you're looking at each one in isolation. I think most important is this element here. So often in bioenergy systems models we say, okay, we've got a certain bit of land that we can use for a variety of things, and maybe we'll classify the land by different classifications like current land use or by grade or by quality and so on, and then we'll say, okay, this agricultural grade land, we can't use it for bioenergy, or we can use 5% for bioenergy, and this less good land we can use up to 30% and so on. So what we often see in these bioenergy system models is what we call these side constraints that sort of restrict how much land you can use because there are these other things that you need it for. And so we were always quite frustrated by that. So we said, why don't we have a model where we model all the different things you can do with the land, and then we set scenarios for the other things you want to do. So particularly food production and then also delivery of other ecosystem services. So we can look at, again, it's a UK perspective because it's a UK funded project. If the UK wants to maintain its current level of food security, how would you optimize the land use if at the same time you also want to deliver X% of energy, be that heat, power, transport, fuel or other, from biomass. So it's internalizing the food production side of the system into a model rather than putting in these side constraints, which are often very difficult to get right. That's a UK-centric picture, so it says if the UK maintains a certain level of food security, what can we do for bioenergy? So that captures all the indirect land use change within the UK. Without the UK, of course, there could be perturbations, and DEC has developed a global calculator that you may be familiar with. And that's interesting because that takes a global picture of land use and it covers all land uses. So it's one of the first models where you can look at the big picture without indirect land use change, because all the land use change is captured in the model. So you can look at how diets evolve around the world, how energy demands might evolve and how much might be from bioenergy. So it's all captured in one model. So it gets away from what I call the theology of indirect land use change, because sometimes the debates around it do sound a bit like theology. So that's what we want to do in this model, and we want to also look at how bioenergy impacts upon ecosystem services positively or negatively. This is how the project's organized. So it's Quite similar to some other pictures you might see, which is about the technologies for pre-processing and conversion, the resource potentials, food and biomass and ecosystem impacts. That's very much around land management, the value chain design, which is modelling, the wider UK energy system, and then the case studies, feasibility assessment and deployment strategy. I'll talk a bit about bioenergy system models briefly for those of you who may not be so familiar about this kind of model. So we have these 5 elements that you need in an energy system model, and bioenergy particularly requires careful consideration of these. So spatial elements, temporal elements, the resources, the technologies and the infrastructure. So time is usually in some kind of multi-scale concept, because you've got decades over which you might evolve the land use, and then you've got a typical year which has variations on the demand side and the supply side because of the seasonality. And if you want to, you can go into even finer detail. Resources, what do resources mean in our modelling framework? They mean primary materials, if you like, which could be fossil fuels or energy sources, but also obviously different kinds of biomass. Or they could mean intermediate things like pyrolysis oil or torrefied pellets. And then, of course, end-use vectors like power, heat and transport fuel. And sometimes we will capture what we might think of as waste as resources, because in other systems we may be able to cascade them and actually reuse them in some other system. So, of course, carbon dioxide utilization is a very hot topic, particularly in continental Europe, where they don't have so much geological storage of CO2. Then the next modelling element is the technologies. And so in our modelling framework, a technology is something that takes one or more resources in and produces one or more resources out. So it could take wastewater and produce clean water. It could take pellets and produce heat. It could take biomass and produce chips and produce pellets. So it's just a generic concept, and we'll see how when you combine these together you get a value chain. They may operate in different modes because, of course, a biomass power plant might be able to run on miscanthus and SRC, but its performance might be slightly different. Then we have the concept of infrastructure, which is primarily to move resources. So it could be a logistics network, including railways, waterways and roads for biomass. It could be a power grid. It could be a district heating network. It could be a water network. And of course, some of these may exist and you can take advantage of them, but if they're not there, you might need to build them. So something like a district heating network with a biomass power plant, it may not exist, in which case the model would have to work out that it needs to be built. So we haven't built this model from scratch. We have built in the past other models from scratch, but what we're doing in this project is we're adapting an existing model, which is a model that was actually developed for the ETI by a number of people, including many of the consortium members of this project, which is called the BVCM project, Biomass Value Chain, or Bioenergy Value Chain project, which is a UK-wide optimization model. It models these pathway-based bioenergy systems over 5 decades, and it has a fairly granular spatial model. And essentially what it does is it takes the data about the system and it looks at answering these questions. What do we grow in the UK, given how much land you make available to the system? What do you convert it into? And how does that change over time, depending on the system constraints? So the model looks like this. It's got a spatial granularity of these 50-kilometer square cells, 157 of them, 2 climate scenarios, looks over 5 decades, quite a large number of resources, I can't remember now, 50 odd, and a large number of technologies. So if we look at land use, the way land is described is by different land categories and by different aggression levels. So we have a number of different categories which are land classifications. They're based on the Corinne database, so different types of land classifications. And then we have these different levels of aggression, and these squares are showing how much land is available for potentially for bioenergy, this is in the ETI model, depending on how aggressive we are. And there are still constraints on slope, organic carbon content and things like that. And clearly, if we had a thing that looked like this, where we make available a lot of land for bioenergy, then we are, of course, potentially running the risk of public acceptance issues. So one of the things we're doing to adapt the model is to look at the question of the ecosystem service impacts of land use change. Now, what we're not going to try to model in this project is absolute values for ecosystem services, because that would be a decadal project in its own right. What we're trying to look at here is when we have a transition, so again, somebody was talking about a transition being, sometimes it's a crop transition, and sometimes it literally is a land use transition. So for example, if we're going from, say, forest to miscanthus, then you can see that there's quite a lot of red in this matrix, which is saying that in a semi-quantitative way is probably not a good transition from an ecosystem service perspective. But on the other hand, if we're going from arable to say miscanthus again, you can see a lot of green. So this is primarily literature based at the moment, and it's based on a kind of set of levels from neutral, moderately good, moderately bad to very good, very bad. So it's essentially mapping out, and the idea is to make this more and more quantitative over time. That if you have a particular transition, what might be the impact on ecosystem services? Now, of course, that can't be a global picture. It has to be representative of the particular landscape. So each location in the UK would have a matrix like this, because it very much depends. For example, if you have an at-risk species, for example, then the biodiversity impacts would be much greater than if it's an area which is like East Anglia, where maybe you have a lot of farmland. So that's the first thing that we're going to be extending. The other one is to bring in this relationship between the wider global and the UK energy system model, which is a set of models being developed at UCL, where we'll be looking at this trade-off. Because again, there's always this big debate. If we grow biomass, what should we use it for? Should we use it for heat? Should we use it for power, transport fuel, hydrogen? And it's very difficult to answer that question unless you do it in the context of a wider energy system model. So in the wider energy system model, it's worrying about how do we serve all of the UK's needs. And it's saying, well, under these constraints, for example, strict carbon constraints, then there is a strong need for bioenergy because we need to meet certain things that we can't do otherwise. And this is what we call a resource technology chain. So it's not very clear, but it gives you an idea for winter wheat through different kinds of processes for both the straw and the grain, how you can end up at a variety of different end-use vectors. So some of the things we want to add are the resource side, like food crops and pasture, non-energy use, and non-energy products like food, livestock products, timber products, and chemicals. So the white bit is what is existing in the model, and this is what the new project is doing. So trying to internalize the other things we do with land, so we can't then have these issues of how much should we use. We can have big picture stuff saying, we want this much timber, we want this much of these kinds of food, maybe some plastics or other chemicals we also want to make, and then the rest is available for bioenergy. So I mentioned ecosystem services. So here again, we can see these are the transition effects, positive or negative, depending on the type of transition. And here we're just looking at a case study, which is suppose you wanted to meet 10% of transport fuel from renewables, of which 6% is going to be met by domestic UK production. And we've got a variety of, we're not being prescriptive on the transport fuels, so we're just saying the total amount, and the model will decide which transport fuel to go for. And that could be from first or second generation crops, and with some carbon constraints. So what happens is, here what we're looking at is we're looking at a set of configurations which are saying that we are, in this case, happy to have some degradation in ecosystem services, which is on the left-hand side. This is the neutral position. And this is saying, actually, we want a bioenergy system that, in its land use transitions, is also having a favorable effect on ecosystem services. And of course, as we start to say, well, we want to go from neutral to positive, we can see that the cost of the system is increasing because we're not cherry-picking the sites. If we look at what happens as well, as we start to push harder and harder on these ecosystem service impacts to make them positive, but what happens is this grey, for example, plots along and then goes down. So that's a first-generation crop. So that's sugar beet, for example. This blue one here is wheat, and again we see that disappearing from bioenergy use, and instead we see an increase, for example, here on this one is long rotation forestry and an increase in SRC willow. as a way of delivering energy services, transport fuel in this case, via different technology, in fact, as we'll see that we transition from ethanol through to second generation fuels which are using those different materials. And in parallel, we still are using the land also for wheat production. So we are still meeting domestic wheat demand at the same time. So that's internalized in the model. And these are just illustrative because the project is only about halfway through. So we haven't actually got all the data sets. So what I'm really showing is what we can do in the model and the kind of trade-offs we can look at. What we're not able to do is to give you definitive results, because that will be much later on when we've got better data. And this is what happens in the system. You can see here that these are the kinds of technologies that you start to need to bring in when you are moving towards second generation technologies, which are pyrolysis and catalytic conversion, either syngas to methanol or pyrolysis oil upgrading. So this is pyrolysis oil being made in a distributed fashion and then sent to some central upgrading facilities, and these are the logistics networks. These are some of the pyrolysis plants, and these are the gasification and methanol plants. This is what the system looks like in terms of production. So it's mainly upgraded pyrolysis oil and some biomethanol, and the production cost of the fuel is a mix of the technology cost for buying the technology operation, and then the crop production cost. So the system is organized so that the logistics and transport is a fairly small proportion of the costs. So that was only looking at some staples, in this case wheat, and there's also potatoes in the model. What about livestock? So what if we include wheat, potatoes, and now livestock in the model? And we say, how are we going to use the land to make what we want in terms of food, but also to look at some bioenergy scenarios again. So this is just the kind of long-term trends in the UK for livestock. So you can see that poultry is increasing, and sheep, pigs and cattle going down a little bit. There's two types. So there's fodder-fed population and forage-fed population. So we have a set of classifications we use in the model. One is a livestock unit coefficient, which is the grazing equivalent of an adult dairy cow producing 3,000 kilograms of milk. So that has a coefficient of 1, and then other types of livestock have a relative coefficient related to that. And then we have another unit which is essentially for a particular type of livestock, weighted against that value of 1, how many can you support over a year per hectare? And that depends again on the feeding strategy. Separately, we also need to model the land use that's required to produce grains, if there is going to be a degree of grain or haylage or silage that's required for the fodder feed. So we need the land which is the forage land of the livestock, and then the additional land for the fodder feed. So we've got the livestock, the land that they're using, the land for the fodder, and of course the other land that we're going to need for things like potatoes, wheat, and other food that we'll also have in the model. So what about bioenergy? Well, we've got a similar kind of scenario here, which is here a cap of 7% from food crops and 10% share of renewables. Again, these are the assumptions of different kinds of cattle. So looking at cattle in a bit more detail, dairy breeding herds and other female cattle, and then how much land you need for forage, or how much land you need for the wheat that provides the fodder. So that can all go into the model. Now, of course, one of the trends that we've seen is a downward trend. So one of the questions is, how will that go out in the future? So you can create scenarios of the future. So you could say we stay flat from the 2010s, or it doesn't go down as fast as the historical trend, or it does go as fast as the historical trend. So these are the sort of user inputs into the system. You can sort of optimize the system under that, and you find things like, in this case, increasing production of winter wheat here, because we actually allow a reasonable amount to be used for transport fuel. This is our land for rotation of grass for forage, for example, going down, and so on. And here we can see the different kinds of feedstock that are being produced. Initially, we have a lot of biomethanol being produced, and then increasingly upgraded pyrolysis oil. The key thing there is we see a gradual reduction in land being used for cattle, and therefore potentially more land being made available if we allow transition from pasture to particular kind of bioenergy crops that can be available for this second generation biofuel production. So, of course, we have to think about what are the assumptions about how diets will evolve in the future in the UK, and what kind of national food security levels do we want to have. This just shows how the system cost actually goes through a maximum because we expect technologies and yields and things like that to improve in the future, and therefore to reduce costs. And this just shows how you can actually see some gradual trends in changes in land use. The colours are not so clear, but you can see increasing production of willow, for example, in Scotland. What we're trying to do, in summary, is to go away from the traditional way in which we've modelled bioenergy value chains, which has always been along the lines of, we have a spatial model of land. We say in each part of the UK how much of that land, given what's going there on at the moment, could we in principle use for bioenergy under different scenarios. We make that land available to the model. The model chooses, depending on the climate, the yields, the technologies that you're going to use, what you might grow there and how you might process it and move it and then make the end use energy system or energy vectors. So what we're trying to do now is to say, well, let's not worry about constraining the bioenergy system. Let's put everything into the model. So the ecosystem services we want, the other products like timber and food, which means dairy, meat and grains, possibly other things as well, sugar beet and oil plants as well, they're in the model as well. Put that all in, say, these are some of the scenarios we want in the UK for those other products. Now you work out, by moving things around the map, what to grow and how to convert it. So far, what we've demonstrated is we are able to consider these things. The big issue, I think, is, of course, that the results are very data dependent and very scenario driven, because even when we are able to pose those questions, we still don't know what the policy objectives will be around things like food security and ecosystem services. So thanks for your attention, and happy to answer any questions.
I just want some clarification. So in the case of miscanthus or willows, for example, any perennial feedstock that requires a take-up time and even the multiplication to actually get those plantations, is that somehow factored into the model?
If you're developing a land use transition, in that first decade, the yields that are accessible to the model have a downlift to account for the fact that you've got essentially a cultivation period and possibly even a cultivar period and then an establishment period. So the first decade is down-rated, so the yields might end up being averaged out over a decade 50 to 70% of what you'd expect in the second decade.
Are you able to represent the scope for improvements in existing land use productivity in the model? How does it represent that?
So there's two ways. So the first is that the database that has the crop yields that are spatially disaggregated, so it has the yields of each crop in each bit of the UK, already includes the expected yield uplifts, which are based on historical data, but also what might come through from marker-assisted breeding and other things like that. Now, if the user wants to be even more aggressive or more pessimistic, the user can then put a mask on top of that and say, actually, I want to downrate those or I want to uplift them. And they can do that by crop and by region. So there's a fair bit of flexibility. So as I say, again, it's a very data and scenario-driven model. So it has all the data in it, which includes the efficiency improvements in power plants, in torrefaction and whatever, or the cost improvements, which are all evidenced and literature-based. So you can just go with the model, but you can actually put your own expectations, whether you want to be aggressive or pessimistic.
Can I just ask a quick supplementary? Do you have a view, a sort of gut view yourself on what the scope is for productivity improvement as a route to releasing and making available land for biomass?
It's interesting because productivity improvement, there's two elements to it. So there's a macro element to it, which I think is well represented in the model. And I think that is what probably a lot of people here would also recognize from the expected yield improvements, both in food crops and bioenergy crops through agronomy practices and so on. But I think what's really interesting, and is not captured in our model because we're another spatial resolution for it, is actually the micro level of landscape management, which is it's a very multi-scale thing. So, you know, we heard Chris's talk about how, you know, that can be done in the context of water treatment. And I think the really big opportunities are in that multiplicity of landscape management opportunities, whether that's in the UK or elsewhere, to develop, you know, what we call high carbon landscapes. So Guts will remember we've been trying to get this project off the ground for I don't know how many years, called high carbon landscapes. But that's a very micro perspective, and that's almost taking every locale and optimizing it, taking into account its peculiar features. And that's where I think the opportunities are really big. The other opportunity is actually to go outside the UK. So I always say to people, if you go and look at a world map, the place to look at is Kazakhstan, and look how much good land, you know, quite appropriate climate, and yet very low yields and very underutilized. And if you just took a place like that and said, let's sort of max out what we can do there, you could really you know, change the picture a lot.
Could you explain what the model really optimizes, what the objective function, so to speak, is?
The objective function is quite flexible. So you can either meet a requirement of food, other products and bioenergy at minimum cost, minimum greenhouse gas emissions, or some combination of the two. Or you could say, I've got this much land and I want to maximize the amount of energy or exergy I create with my pathways. So again, it's quite flexible depending on what picture the user wants to put together. And so normally we would definitely recommend that anybody doing this kind of analysis would look at different kinds of objective functions and see what kind of insights come out. Because if you want to just do cost, for example, you might end up with a biomass to heat pathway, because that's a fairly low cost way of delivering a lot of energy. But another thing you can do is actually maximize value added. So if you go in a maximized value added pathway, you might end up making a lot of aviation fuel as your final product. And so one of the questions is, you know, both of those are potentially quite valid. That's why we also like to couple with the UK energy system model, which might give some insights where bioenergy is most useful.